So this is the first lecture for CET236. Sorry, the second lecture for CET236, the first video. And it's about the second week contents. Before coming to class, I hope you reviewed this video and had a look at the textbook about it. Maybe the some of the same topics in the Khan Academy videos that I shared through Blackboard. During this class, we're going to be doing a lab about measuring resistance. We're going to talk about last week's content and this week's content, and we're going to be doing some problem solving. I'll probably do a bit of lecturing on the board as well, but I'm hoping to use some of that time here rather than during class. So here's our semester. We've done the first line there, the orange line. Today's topic is series, parallel and combination series parallel circuits. And then the lab is going to be the resistor code, color code and measurement. Here's the overview and the progress. We've already talked about voltage, current, resistance, power and energy. And this lecture and lab we're going to talk about series circuits, parallel circuits, combination series and parallel circuits, Kirchhoff's voltage law, Kirchhoff's current law, and the lab will be about a use of a digital multimeter. If I have time, I'm going to talk a little bit about voltage dividers and current dividers also. So, series circuits. As this slide says, two resistors, in this case, are connected in series if they share one node exclusively. That means there are no other devices or elements connected to that node between R1 and R2. And if that's the case and they're in series, then we can redraw R1 and R2 as a single resistor, and the resistance of that single resistor is just R1 plus R2. One thing to note about when elements are in series, that means that they share the same current. The same current has to flow through both of them. So in this case it says IR1 equals IR2. So the other configuration we want to talk about today are when they're in parallel. And two elements are in parallel when they're connected between the same two nodes. And here in this diagram, R1 and R2 are connected between the same two nodes. The line at the top of this is a node, and the line at the bottom is a separate node. Now, parallel elements are a little trickier than series elements. So, because they may not be necessarily drawn as if they're geometrically in parallel. Here, R1 and R2 are connected between two nodes again, but they're not drawn as if they're in parallel. They're drawn like they're at right angles. But in this case, the devices, the elements, are in parallel. The other tricky thing about parallel circuits is that just because two elements are drawn as if they are in parallel, they may not be connected in parallel. Here, R1 and R3 look like they're in parallel, but they're not because they're not connected between the same two nodes. This circuit has three nodes, the one between R1 and R2, the one between R2 and R3, and the one at the bottom between R1 and R3. And similarly, R1 and R2 are not in parallel, even though they're at right angles, because again, they're not between the same two nodes. Here's a circuit that is a combination of series and parallel resistors. This one's taken out of the fall 2017 first midterm, so you can expect something like this on the midterm that we'll have in a few weeks. The thing about this is there are several things in parallel and or series. So the way to approach this is from the right hand side of the diagram, and you can see those three 3-ohm resistors. And believe it or not, even though one of those 3-ohm resistors is on a diagonal, those three 3-ohm resistors are all in parallel with each other. So we can put them in parallel, and if we put them in parallel, then the total resistance of the three of them together is 1 ohm. If we then replace those three with a single resistor of resistance 1 ohm, then that 1 ohm resistor is in series with the 5 ohm resistor at the top in the middle. So the series resistor, 5 ohm resistor and 1 ohm resistor sum to a 6 ohm resistor, so we can replace that 5 ohm plus 1 ohm with a single 6 ohm resistor. If we do that, then we have 3 6 ohm resistors in parallel, and that sums up to 2 ohms. Then we have a single 2 ohm resistor in series with a 5 ohm resistor. So that means the total resistance between node B and node A is 7 ohms. Okay. So another thing we need to talk about, that we talked about last week, but we need to talk about again, is the two Kirchhoff's laws, Kirchhoff's voltage law, which says that the algebraic sum of the voltages around a loop in a circuit is identically 0 for all time. And if you remember, we talked about what would happen if Kirchhoff's voltage law didn't hold. If we went round a loop in the circuit and the voltages didn't sum to 0, if we went round it again, say they summed to 10, if we went round it again, they'd sum to 20, and then we could go round it again and it'd sum to 30, etc. And we'd have a infinite power for no input. So Kirchhoff's voltage law has to hold. Similarly, Kirchhoff's current law says that the algebraic sum of the currents into a node at any instant is 0. And here the issue is, if it didn't hold, then if the algebraic sum was non-zero, then we could get an accumulation of charge in a normal circuit, which is not going to happen. So that's Kirchhoff's current law. I'm going to skip ahead a little bit, at least in this video. We'll backtrack during the lecture on Saturday. I want to talk about voltage dividers. Right? Here's a simple circuit. It's got a battery with 15 volt supply. It's got a current I, and it's got two resistors. It's got a 10 kilo ohm resistor and it's got a 20 kilo ohm resistor. And the idea is that we want to figure out what the voltage across each individual resistor is, given that the voltage supplied is 15 volts. Now, one tricky thing about this is you'll see that in some ways the battery, the voltage supply is upside down. That is, the positive terminal of the battery is at the bottom on the left-hand side. So that means the current defined on this is sort of going the wrong way. because normally the current is defined to flow from the positive terminal of the battery to the negative terminal. So really the one way to deal with that is to say, okay, well, let's flip that battery so that the positive is at the top, but then the supply is going to be minus 15 volts instead of plus 15 volts. The way to do this is to say, okay, just use Ohm's law. Well, first of all, note that R1 plus R2 is they're both in series, so the total resistance in the circuit is 30 kilo ohms, and that means we can apply Ohm's law, V equals IR, although we need I, so that means I equals V on R. So V is 15 volts, R is 30 kilo ohms. So what's that? That means that the current is half a milliamp. And if it's half a milliamp, that means that the voltage drop across R1 is going to be 5 volts, and the voltage drop across R2 is going to be 10 volts. Now we've got to be careful with the signs, which I'm not going to do on this video. I'll go through it in class. But the check is to look at this and think about Kirchhoff's voltage law. So this is a loop, and if we know that the sum of the voltages around the loop have to be 0. So if Vs is 15 and Vr1 is 5 and Vr2 is 10, that'll tell us something about the signs, because 15 minus 5 minus 10 will be equal to 0. So for Kirchhoff's voltage law to apply. And we can do the same sort of thing with current dividers instead of voltage dividers. And here we want to figure out, we've got a current supply of 3 milliamps, and we want to know how it splits between the 5K resistor and the 10K resistor.